Well, thank you everyone so much for being here. We are going to get started. This is the 5th MEV-SBC, the MEV workshop at the Science of Blockchain Conference. First up for session 1, we have Muriel Médard. Muriel is the co-founder at Optimum and also the NEC Professor of Software Science and Engineering at MIT.
Thank you so much. Can I borrow that? Thank you so much. Thanks. Yeah, thanks for coming. I can tell, it's early in the morning, but here we are. We're going to be Optimum together. I'd like to mention my co-authors, Kishori Kanwar, my former postdoc, who is now our chief scientist, Moritz Grande, and my former student, and Vipindev Vasudevan, who is also my former postdoc, all at Optimum. Okay. So what I'm going to talk about today is a peer-to-peer broadcasting. And the reason I wanted to bring this up is because there's a lot of discussion right now, rightly so, in the community about, how do we make things go faster? And one way of making things go faster is to use, say, dedicated links like fiber and so on. I've worked in fiber for a lot of my career. I love fiber, but it can only do what it can do. And so the question here is, can I speed things up, not just without fiber, but also effectively leveraging whatever speed dedicated links certain people have, invested in, and give a wider gain to the system. Okay. Now, when you look at gossip, there's sort of two different paradigms, effectively. One is the unstructured mesh, which is probably what we think of more as gossip. Each node connects with most peers. You have a multi-hop propagation. It introduces loss which may not be full loss, but just delay, things not getting there on the right time. And that becomes the bottleneck. Most familiar example would be Ethereum gossip sub. And, the other approach, which is more, let's say, a hierarchical approach, either a tree or some other hierarchical graph, where you have a source that's talking directly to the sinks. Okay, so on the left-hand side, you have, if you will, the most structured that you could think of, like, exactly, who's talking to whom directly. And on the right-hand side, you have, if you will, the most unstructured you can think of, right? Now, at Optimum, we've been working right now on the right-hand side, which is basically, how do I optimally disseminate, and we have results there, and we use randomly network coding. I'll tell you in a little bit what that is. But also what I wanted to do is go to the left-hand side, because to some extent, I've already talked about the right-hand side, and it's maybe clearer why coding is very important. But maybe on the left-hand side, it's not as clear. Okay, so when we talk about coding here, we're talking about coding against erasures. And again, an erasure may not be that, a shard is lost forever. It may just be that it didn't get there on time, right? So erasures think of, failures to behave the way you wanted it to behave. Let's put it that way. And, there are different ways of looking at this. So at the bottom, you have sort of the most raw fashion, which is unsharded. Okay, and you have an arrival of shards at a rate which is usually denoted by lambda, using the customary queuing notation. You can, of course, shard it and leave it uncoded. Those are those orange little pieces, right? So now you have these shards. Each of these streams is basically now has a lambda over k. If k is your sharding factor. Or you can code. You can use structured code, a fixed rate. You can use a Reed-Solomon, which I denote by RS. You can use Blas-Chaudhuri-Hockenheim code. You can use a Reed-Muller code. You can use whatever code you looked up in Lin and Costello by grabbing, some random page on it. Whatever code it is, they tend to be systematic. What systematic means is that you first send the data, and then you send what's often called redundant, but I like to call it repair, because redundant makes it look like it's no use for anybody. And now what you do is you take these k shards, and you expand them into n shards. So you have n minus k redundant shards. You can also do, so basically this would be something like what Solana does. Okay, so if you look at Turbine and now Rotor coming online, they use Reed-Solomon codes. Or you can use rateless codes. So this would be something like what Monad does. Okay, so they use Raptor codes, where you have a structure on that green part, but you basically send only as much as is needed. And then you can use random linear network coding, which is you can use as a fixed rate, you can use as a rateless, but we're going to talk about it today as a rateless. You just you send random equations out of those k shards that you started out with. Okay. All right. So if you're doing multicast over any network, the only code that is optimal for any network in any network is RLNC. Right? All the others are suboptimal, and actually they're suboptimal in an exponential way. That's to say that as your network becomes larger, the structured codes have a performance that goes down actually exponentially. So it's not slightly suboptimal, it's disastrous. Okay, but if you have maybe a very small network, maybe that's okay with you if you don't want to scale up. So now what we have here is we're going to do recoding. And the recoding means that the RLNC system is able to take any code, including structured codes like a Reed-Solomon, and say, well, okay, a Reed-Solomon code is just a random linear network code that was having a bad hair day. It's okay, I can use it, okay? And I can recode on it. And that's really what we're going to use. So we're saying, okay, Reed-Solomon code is just an equation. It just happens to be a highly constrained equation because it came from the 1950s. But I can, upgrade it to a more more versatile type of equations. So we're going to have code-agnostic recoding. Okay, so I can recode something that was not coded, something that was coded with a legacy code. I can always recode using RLNC and say the output is always RLNC. I'm not going to coordinate the shards, right? One of the reasons for coding is otherwise you run into the coupon collector problem, which means that if I have k shards, I have to recover those exact k shards. If I get 2 copies of shard 2, it doesn't make up for my not having a copy of shard 3. Make sense? And the decoding is always Gauss-Jordan elimination. Okay, the decoding is super easy. All right. Okay, so the problem often with coding is that when you start to try to analyze it, you very quickly run into just horrible combinatorics issues, right? Very, very quickly. You're trying to figure out, particularly when using a structured code, it's like, how many copies of this particular equation do I have versus that equation, together, are they independent or not? It becomes very hairy. So the way we're going to get around that is we are going to use a fluid approximation. And what I'm going to do is the following. I'm going to consider an amplification alpha of the bandwidth, maybe because I have fiber, maybe because I have some dedicated links on AWS, or whatever you did, okay, to get, you had to go in your pocket and pay extra money for it, but whatever you did, you got more bandwidth, right, by a factor of alpha. Does that make sense? And of course, that you then have to share among the different sinks. That's to say that even if you go, well, but I had a fiber to go into each of them. Yeah, well, you had to pay for it that many times, okay? And you have to share it among M sinks. And M sinks may be basically, if you think of a proposer being the source and a sink being the validator, that would be basically how many validators is the proposer talking to. Make sense? Okay. So if I look at a fluid approximation, and I look at the fraction of nodes that have at least I degrees of freedom, right? So if you think really of this in terms of linear algebra, and you say, this is the dimension of my subspace is at least I, right? And of course, when I is equal to k, I shout bingo, and I'm able to decode using Gauss ordinary elimination. Everybody happy about that? Right, I'm trying to get I to be k, okay? So I can show you in terms of steps, which are denoted here by S, so F is the fraction, that basically I can have a fluid approximation where from one time to the next, of course I never lose degrees of freedom, okay, so F of S plus 1 is always at least F of S, but I also gain degrees of freedom here coming from the source. At a fraction, basically alpha over m, where there's some p, and p is a probability of not losing, the probability of getting through, right? Remember, we have an erasure code, you have a probability things did not get there on time as you wanted them to, okay? So p is the probability of success that didn't happen. And you can show a propagation front. Remember, you were trying to get to k to be I. Here, I to be k. Here you have a k of 32. So when you have 32, you go, OK, I can decode. So you have basically these time steps, this number of unique shards, and then you can see the percentage of pairs with at least I unique shards. Does that make sense? So I want to get to some percentage, depending on what your mechanism is in your protocol. Typically it's 2/3, right? Because you're trying to get to consensus. So if you go, okay, I'm trying to get to consensus, I want to get to that sort of green, which is going to be about 2/3, right? And once I get to 2/3, I'm happy. If I want to get to everybody, then I have to get to yellow. Make sense? All right. Any questions so far? That's good. Yeah?
I guess I can just say it. So what network assumptions is this making? Like if these links are adversarially controlled or lossy?
They're not adversarial at this stage. We can talk about adversarial later, but it's just, you know, you're just getting delays. But we can talk about adversarial later. I'll
Okay, and one more question. So the distance between the green and the yellow seems pretty small.
Yeah.
Is there a theoretical reason for that? Okay.
Yes and yes. And you're going to see an even smaller. Okay? So now I'm going to allow the sinks to help each other out. Now, whatever coding was being used, I'm now using an RLNC system to have the nodes talk to each other. The sinks, okay, the validators are helping each other out. Does that make sense? Because they have to recode, and the only recodable code is RLNC. So they might have been getting codes that were, you know, they might have been getting shards that were Reed-Solomon code, that were whatever code, but now the recoding is always RLNC. And what I want to point out is I can still write an equation, but the really important thing is the following. The different term that comes now, which is these nodes, which, by the way, don't have fiber, so they have a weak link among them. Okay, they have weak links, okay? They're not exchanging a whole lot of information. But they're basically using equations to get everybody to the level of the winner. That's what coding does. Right? Coding here is about order statistics. And what you're doing is you're bringing everybody to be the winner of each race. Everybody to the same level. It's that extra term, the turbo. So we call it turbo. Why do we call it turbo? It's not like turbo codes. You can look them up online. Those are different things. It's turbo because you're using stuff that was already in the system and you're recirculating it like an actual turbo engine. Does that make sense? Right? You're using stuff that was already in the system and you're recirculating it. Now what will happen is that you're going to get this extra element which is not reduced by m, right? Remember, but what was happening before is if you, as m, which is the number of sinks, number of receivers goes up, you were getting that this evolution was really slowing down. And here you don't have that anymore. Sorry, there was some issue which does not show up. There should be an f sub I s plus 1 on the left, but somehow that didn't translate. Okay, so now if you look at the scaling behavior, what do you see? So as I vary the source bandwidth here, that means that 50 means I have a 50-fold multiplication in the bandwidth. Okay, so 50-fold means that basically you went out and you bought 50 times more bandwidth. That's a lot of money. Okay, or 100-fold, or even 500-fold. What you can see is with turbo, right, you get to this, actually you get to 1, to your point, 100% pretty much right away. That green part goes away, okay? And you get to 2/3 very, very quickly. And if I vary the number of receivers, so if I only have like 10 receivers, as I said, if you notice, if your network is very small, sure, go ahead, use whatever, okay? If you only have, if you're only trying to establish, let's say, consensus among 10 nodes, that's fine. But now, as you go to larger numbers of nodes, the difference grows massively, right? Literally, the difference between using turbo and not using turbo, even if I have a pretty non-trivial gamma, alpha, I'll show you gamma in a second, which is this amplification, is huge, okay? So again, this goes back to what I was saying. It's not like, oh, well, could I use this other code and it's not quite as good. No, it's not just not quite as good. It's deathly bad. Okay. So what happens if not everybody is accelerated, right? Remember, my argument is you get everybody to be a winner. So here I'm going to have some gamma where a fraction have that amplification, those fiber, and the others don't. The fraction 1 minus gamma. Make sense? So not everybody is amplified. Well, even then, with turbo, pretty much everybody gets back to being the winner. That effect, that disseminating effect, is extremely strong. So even if 20% of them don't have fiber, it's as though everybody did. You cannot even see it. Does that make sense? So you get to free ride on whoever actually put in that bandwidth. Okay? Very, very strong results. Okay, so the latency goes down like crazy. The fiber, non-fiber gap collapses to near 0. And there's no coordination, right? The code is entirely stateless. As a matter of fact, even if you told me the state of the other nodes, I wouldn't use it. There's nothing for me to do about it. Like literally, I just don't care. So you could tell me, oh, this node got these shards and that. I'm like, I literally, I don't care. Like, just give me an equation. The others don't matter. Okay, so obviously this has MEV consequences. I mean, first of all is, of course, the latency, right? We all know slot propagation leads to misattestations. It's an issue, etc. Here you can see that, of course, it improves fairness. Pretty much everybody's at the same level in terms of receiving. Everybody has the same chance. And of course, very importantly, is the scale, right? So I don't need to sort of constrain my number of nodes artificially because otherwise, I'll never get done. You can scale in a completely different way. And now I'm at 0 minutes. And if you're interested, little QR code, go online. Thank you. Great. Any other questions? I can maybe answer a little bit your question about the adversarial. So the fluid approximation would not work for the adversarial, but there are other results, actually not by me, by my former student, Bernhard Hoppler. He went to CMU later to be a CS professor. And he showed that RLNC is also optimal in an adversarial setting. That is to say that even, and this goes back to what I was saying, even if somebody came and told me everything that was going on to try to do any sort of game, you would still not do better than this. So it is also competitively optimum against any adversarial erasure game.
Is it more of an uplift than in the non-adversarial, or it's the same kind of thing?
So I haven't done the analysis because there you would start to run into these combinatorial issues I mentioned. So, so it's like you don't know what the performance is, but you know that it would be optimum. That's what it says. Does that make sense? Which is a different matter, yeah.
Yeah, I'll check it out. Maybe we can throw an LLM at it and it can do the...
Pardon?
We can throw an LLM at it and maybe it can do the combinatorial part, you know.
Maybe I haven't tried. Hey, you know, go for it. Yeah, absolutely. Thank you. Thanks.